Hello and welcome, and this video will serve as an introduction to graph theory. So a graph is defined as a two-tuple containing a vertex set and an edge set. And just to make this easier to understand, I'll draw an example of a graph. Let's say we have a vertex A, which is connected by an edge to vertex B, and both of these vertices will be connected to C by two other edges. So the vertex set for this graph in particular will be the set containing A, B, and C, and the edge set will count all the edges connecting them. So say edge set is equal to the set containing, first we have the edge AB, that is this thing right here. And since the order in sets don't really matter, this will of course be the same thing as the set BA, but that's not counted twice. And this has the edge AB, BC, and CA. So a graph could really look like anything, could look like this, for example, just as long as you have vertices and edges connecting those vertices. Let's label that again as A, B, C, D, E, F for this graph. Let's move on to a definition. We say that the valence of a vertex is denoted as delta of said vertex is equal to how many edges it is connected to. So if we want to say, in this case, the valence of B will be equal to 4, since it is connected to 1, 2, 3, 4 different edges, and the valence of the valence of D will be equal to 2, since it is connected to 2 different edges. Now let's move on to what's known as the handshaking lemma. And the handshaking lemma says that the sum of the valence of every vertex of the vertex set is equal to 2 times the amount of edges a graph has. And let me just give you some intuition about this. Say we have a graph that looks something like this, maybe. Call it A, B, C, D. And A will have a valence of 2, B will have a valence of 2, C will have a valence of 2, and D will have a valence of 2. So, and each edge will be marked 2 different times, because the definition of an edge is a connection between 2 different vertices, and the valence of a vertex is defined by how many edges it is connected to. So each edge must be marked exactly twice. Say the edge edge AB. AB will be marked once to add to the valence of, it will be marked once to add to the valence of A, and once again to add to the valence of B, and the same logic can be applied to every other edge we have. Just as an exercise, you can attempt to draw a graph where this does not apply, and hopefully you'll understand why this must always be the case by seeing that it's impossible. And yeah, this was just to give you an intuition about why it works. More formally, we can prove this by attempting to count the elements in the set we'll call X, which is equal to the set containing the two tuple of vertices and edges, where said vertex is an element in the edge, which of course would be a subset of the Cartesian product between the vertex set and the edge set. There will be two different ways to count the elements of X. The first approach is to say that every element of X can be calculated by delta of V for every vertex, since that will count every edge a vertex is connected to. Hence, those two tuples will belong in the set, since that was the defined criteria. Or yeah, so the first approach is just to count this. The other way is to count the elements in X. The other way to count the elements in X is to say that every edge must have two vertices as its elements, purely due to how an edge is defined. So each of those vertices must be included as pairs with said edge in this set of two tuples. So this will be equivalent to 2 times the edges, which is what we said. Let me just give you an example to make this easier to understand. Say we have a graph that looks like this. Say this is vertex A, vertex B, vertex C, and vertex D. And now, if X is supposed to be the set of two tuples of vertices and edges such that the vertex is an element in said edge, we can count this as the set containing, first, let's say we have two tuple of A, which is connected to the edge AB. We have the two tuple of B, which is connected again to the set AB. We have the two tuple of this vertex B, which is connected to not only AB but also BD, and B is also connected to the edge BC. And edge C is only connected to one edge, which is edge BC. And finally, vertex D is only connected to one edge again. Vertex D is only connected to one edge, namely BD. So of course, there will be two different ways to count all the elements of X. first is just to see that vertex A is only connected to one edge, vertex B is connected to 1, 2, 3 edges, vertex C is connected to one edge, and vertex D is connected to one edge. So yeah, A is connected to one edge, B is connected to 3 different edges, C is connected to one edge, and D is connected to one edge. But another way of counting the elements of the set is to see how many elements, how many vertices a said edge is connected to. Say we have the edge AB, which is connected to A. We have the set, we have the edge AB, which is connected to A, and AB is also connected to B. The edge BD is connected to B, and the edge BD is also connected to D. The edge BC is connected to B, and the edge BC is also connected to C. So the other way to count elements in X is to say that every edge must have 2 vertices as its elements purely due to how an edge is defined. So each of those vertices must be included as pairs with said edge in this set of 2 tuples. Since that's just how an edge is defined. So edge BC will be counted twice since it is connected to both the vertex C and B. Veg BD will be counted twice since it is connected to both the vertex B and the vertex D. And the edge AB will be counted twice again since it is connected to both the vertex A and the vertex B. And therefore, we can clearly see that the sum of the valence of all vertices in the vertex set will be equal to 2 times the amount of edges. So let's demonstrate an example where we could use the handshaking lemma. Suppose that April and Brian are a married couple that casts a party with 4 other couples, so a total of 5 couples, which is 10 people. At this party, people shake hands with each other, and no one shakes hands with their spouse, and no one shakes hands with themselves, obviously. At the end of the party, Ryan asks everyone how many people they've shaken hands with, and he receives 9 different answers. No one he asks has shaken hands with the same amount of people. The question is, how many people did April shake hands with? And at first it looks like we do not have enough information to answer this, but we do actually. So since no one is shaking hands with their spouse, and no one is shaking hands with themselves, obviously, the maximum amount of people someone could have shaken hands with is 8. However, since Brian receives 9 different answers, we could view this as someone shaking hands with 0 people, someone shaking hands with 1 person, someone shaking hands with 2 people, someone shaking hands with 3 people, and so on up to 8. Since it's Brian that's asking, we don't know how many people Brian have shaken hands with, but we'll just label him as B. Now, with this given information, we can actually figure out who is married to who. So, since 8 has shaken hands with 8 people, it means that he has shaken hands with everyone from 1 to 7 and Brian, since that's the only way to make 8. And clearly, he cannot have shaken hands with 0, since 0 has not shaken hands with anyone. So if 8 had shaken hands with 0, their number would no longer be 0. So from this, we can see that clearly 8 cannot be married to anyone from 1 to 7 or Brian, since that would violate the rule that no one shakes hands with their own spouse. So therefore, we know that 8 and 0 are married. Or let me just write AM, which is short for are married. And now we can also figure out who 7 is married to. So we know 7 has not shaken hands with 0, since they shook hands with 0 people. And 7 has not shaken hands with 1 either, since 1 received their only handshake from 8. So 7 must have shaken hands with 2, 3, 4, 5, 6, 8, and Brian for a total of 7 handshakes. So the only people he hasn't shaken hands with are 0 and 1, and we know that 0 is taken. This means that 7 must be married to 1. So 7 and 1 are married. And we can continue to just apply this logic our way down the chain. So 0 hasn't shaken hands with anyone, 1 has received their handshake from 8, and 2 has received their handshake from 7 and 8. So therefore 6 must have shaken hands with 3, 4, 5, 7, 8, and B, 7, 8, and Brian, since those are the only alternatives that are left to give him handshakes, and since 0 and 1 are taken, this means that 6 must be married to 2. And we'll continue down this path, and we see that 5 cannot have shaken hands with 0, who hasn't had any handshakes. 1 received their handshake from 8. 2 received their handshake from 7 and 8. And 3 received their handshake from 6, 7, and 8. So, therefore, 5 must have shaken hands with 4, 6, 7, 8, and Brian, since those are the only alternatives that are left. And therefore, 5 and 3 are married. And finally, now, who is 4 married to? Well, 0 doesn't have any handshakes, so we can cross that. 8 received their handshake. 1 received their handshake by 8. 2 received their handshake by 8 and 7. 3 received their handshake by 6, 7, and 8. 4 can't shake hands with themselves. So 4 must have shaken hands with 5, 6, 7, and 8. And we know that 0, 1, 2, and 3 are all taken. And this means that Brian is the only person left whom 4 has not shaken hands with, whom is also not taken. So therefore, 4 must be married to Brian, and Brian are married. But the question was, how many people has April shaken hands with? But since Brian is married to this 4, then this 4 must be April. So the answer is April has shaken hands with 4 different people. You could actually view this as a big graph with as an edge set, say 8 has shaken hands with 1, 8 has shaken hands with 2, and so on till 8. Brian has shaken hands. So we could view this as a big graph where all of these are edges that are not elements within the graph. But anyway, the answer is 4. April has shaken hands with 4 different people.